Welcome to the video lecture on simulation of solid-state drives using MATLAB Simulink. In this video, let us try to simulate the DC machine in an open-loop environment. So let me try to take a new Simulink model, create it as a blank model, go to the library browser. Let us take a DC machine which is available on the Simscape, electrical, specialized power systems. In that electrical machines, I have a DC machine. I drag and put it on the screen. Double click on this DC machine, you could able to get a configuration which is a preset model as you know. If you drop down this box, you could able to find out lot of models of a machine. Let me take the first model which is a 5 HP, 240 volt armature voltage, 1750 RPM, field voltage of 300 volt. Let me select this machine, click apply and do OK. So there is an armature and there is a field. So let me try to excite this armature and field separately by a DC source. DC source is available in the same specialized power systems. Source, DC source. I need two sources, one for the armature and other for the field. So let me take two sources and connect the two sources to one to the armature and other to the field as shown in this simulation. So from the Simulink diagram itself, you could able to see field voltage is to 300 volt and armature voltage is 240 volt. So this is an armature voltage. Double click, change that to 240. Click apply, do OK. And field 300 volt. Double click, give 300 volt, click apply and give OK. Now I need to have a power GUI in order to simulate the sim power system elements. So I have taken this power GUI. Now let me go to Simulink. In commonly used, you have a bus selector. Let me drag and put it on the screen. This bus selector is needed to connect the measurement parameters of this DC motor. So let me connect these two. So if you double click this bus selector, you could able to see that there are 4 different parameters which can be measured from this DC motor Simulink model. So let me add all these 4 components into the output section. This signal are not needed, so let me remove these 2 signals and give apply. Now you could able to see now the bus selector is having 4 terminals. So let me little bit expand this bus selector so that I could able to connect scopes to visualize the readings of it. So let me go to sinks. I have a scope. Let me connect the scopes to all these 4 terminals. The first one is the speed in radians per second. Second one is the armature current in amperes. Let me little bit elaborate this. And the third one is the field current in amperes, and fourth one is the electromagnetic torque generated by the motor in Newton meter. So these are all the 4 signals which is coming out of this measurement block of this DC machine. So now let me, this speed is in radians per second, but whereas I require a speed in RPM, so for which I go to commonly used, go to a gain block and connect it. You know that omega is equals to 2 pi n by 60. This is in omega. I want n. So what is that I am supposed to do? I want to multiply this omega with 60 and divide it with 2 pi. So 2 into pi. So this will give me omega n. Omega is converted into RPM. So in order to look into the value of RPM, I connect a display box which is available in the sinks. So let me connect it. Now I require a load torque component. Load torque component is a torque which is demanded by the load. So for which I have a constant block. Take a constant block, connect it to the load torque. Okay, now everything is completed. Let me assume that the load torque is some 10 Newton meter. Load torque is in 10 Newton meter. Click apply and give OK. Now this is set to 300. This is set to 240, which are all rated values. So based on the load torque, the machine speed should run at 1750 RPM, which is the motor rated speed. So let me run the simulation. you could able to see that the speed is at 1997. So load torque is less. So let me increase the load torque to 15 and see what is happening. Again run the simulation. 1878. So again the rated RPM, to match the rated RPM, still I want to increase the load torque. Let it be some 18 and check the speed. Again run the simulation. It is 1806. Again the rated RPM is 1750. So I'll increase it little bit, 20 Newton meter. Again the load torque is 1758. So slight increase now, 20.3. 20.3 will give me approximately, yes, it is around 1750 RPM. So by varying the load torque, we could able to see that the speed increases or decreases. So increasing the load torque will decrease the speed. Decreasing the load torque will increase the speed. That is by keeping the armature and field remaining constant. Now this is this rated RPM, now the machine is running. Now what will happen if I reduce the voltage? Some 240 volt, let me give 200 voltage. So reducing the armature voltage should reduce the speed. Now look at this, it is running at 1766, 1366, 76 RPM. Now let me increase it to 210, increasing the armature voltage. Look at this, there is a slight increase in the speed. So reducing the armature voltage is reducing the speed from rated RPM. Similarly, this is what we call it as an armature control. I do not vary the field. Field is remaining fixed. I do not vary the field. Varying the armature voltage from the rated value to a value less than the rated value is decreasing the speed. So let me again go back and keep the armature voltage again at the rated value and run the speed control. Now again it is running at the rated speed. Now let me reduce the field voltage. Field voltage from 200, I give some 270 voltage. 270. From 300, I am reducing it to 270. Now let us see what is happening. The speed is increasing. So decreasing the field current, field voltage will decrease the field current, which in turn increases the speed, because speed is directly proportional to armature voltage and inversely proportional to the field current. So now let me cross check this by having 300 volt again. 300 volt, run the machine. It is running at 1750 RPM. Let me have this field current also here. Field current, let me monitor the field current. How much? It is 1.067. So field current is 1.067 under rated condition. Now let me decrease this field current to 270. 270 will decrease the field current, which in turn increases the speed. So speed is directly proportional to armature voltage, whereas it is inversely proportional to the field current. Now I can do some sort of an exercise here to fill out and find out the open loop characteristics of this DC machine. Let me give a small documentation part to understand this simulation in the form of a data. So this is the documentation which is you are supposed to fill it out for this experiment 1. And look at this. First, you want to have the field voltage at the rated value for 3300 volt and load torque also fixed at 20.38. Vary the armature voltage. From 240, you reduce it and observe the speed. This is the first experiment they were supposed to do. The second one is keep the armature voltage constant and load torque also constant. Vary the field voltage. Reduce it from 300 to maximum value, from 300 to lowest value, and observe the speed. This is a second exercise. And third exercise is keep the armature voltage and field voltage fixed. Vary the load torque from 20.38. Reduce it slightly and increase it slightly and find out the speed in RPM. This is the third exercise you are supposed to do. So these 3 tables you are supposed to fill it, and this is what we call it as open loop simulation of the Simulink using MATLAB Simulink. Thanks for watching this video, and in next video we will try to look into the closed loop simulation of the DC machine using converter by using MATLAB Simulink. Thank you for listening.